Hello, current and or future agronomy 354 lab students. Today we're going to do some exciting, exciting stuff. We're looking at cation exchange capacity, exchangeable acids, base saturation, some pretty important subjects when it comes to the soils of our wonderful agricultural state. So I'm going to kind of step through real quick here some of the slides we were looking at in class, but you guys were chomping at the bit to engage in some exciting science, so may not have paid attention, so we're going to go review those again real quick. Uh, First little batch here, this would have been the first of our two soil shaking labs to this point. We weighed out some soil of a known mass. Hopefully we did that at a pretty accurate basis. We labeled some test tubes with the different soils. If you recall, we're working with both a Hamlin and a Sparta. They have some pretty distinct, just kind of physical properties in the hand. You can feel some higher sands in the Spartas, as well as different color. The Spartas were kind of that yellowish brown, as opposed to the kind of richer dark brown black of the Hamlin. We added a compound. It had that kind of ammonia smell because it contains ammonia, called Malic 3. Recall that that was effectively displacing all of our base cations of interest and replacing them in the soil matrix during that shaking process. We spun them down to keep the soil colloids out of our solution. So we could pour through our filters, capture that filtrate. And then if you recall, this is the stuff that I kind of took care of with the small pipetter, just diluted into some DI water. And then we analyzed on that device the atomic absorption spectrometer. The first of the three base cations, calcium, magnesium, and sodium, we used in absorbance, and then potassium, just by product of how we have that machine configured, we used an emission, just so we don't have any confusion down the road. So those small samples, this is where we dipped the straw, sucked a very small quantity of that solution, that diluted 10-to-1 solution, into that flame that was being driven by primarily acetylene and compressed gas. Each of those atoms were burned at a pretty consistent aerosolized manner, causing some of the light at a very specific wavelength attuned for each of these base cations to be absorbed, and then that is detected by some sort of photodetector. So this machine was calibrated. In the case of section 2, we did this all together. The other section, we just did one of these curves to fill out the potassium that didn't quite work in the first section. But this is where we were taking known concentrations that were made by Teresita Ono, one of the wonderful scientists in our department here, and running them against the absorptions or emissions values for the corresponding base cations. That allowed us to create basically a line, so a regression equation. I used Google Sheets. Microsoft Excel does the same thing. And we just rearrange that equation so that we can input our various unknown concentrations with our known absorbances that we derive from the atomic absorption spectrometer to give us those concentrations of interest. That's really what we're going for here. The absorbance is just a method that we can use to understand what the concentration is based on the relationship from this line. So again, machine outputs an absorbance value. We use this, place that as X in the equation, and we solve for Y for the concentration. So this example is for calcium. I say this is an example for calcium because obviously the sample itself here is what we're going to be hopefully inputting in from our line formula. All of them had the same dilution. All of them had the same extract and soil volume and mass ratio. This is just a unit conversion from liters to milliliters. And then specific to calcium is this ratio here, 20 milligrams per 1 mil equivalent. That might potentially ring a bell. So calcium atomic weight is 40, but it has a valence of 2. So you just divide those across and you end up with this 20 milligrams per 1 mil equivalent. So this gets everything on the same playing field, irrespective of valence. So magnesium atomic weight is 24.3 roughly, valence of 2, so you just divide that in half. You end up with 12.15. Sodium, for example, 23, potassium, 39.1 for atomic weights. Both of those have a singular valence, so those are the same in milligrams per mil equivalent. And then we scale everything to per 100 grams of soil, getting us to this mil equivalents per 100 grams of soil. It's kind of a standard method. You might also see sometimes moles or centimoles per kilogram. It's the same ratio, just depends on the discipline that you're kind of discussing this with. Also, the values are the same, so it's convenient. You'd sum all those up and you'd arrive at some total exchangeable bases in milliequivalents per 100 grams. So you do this for each of the 4 base cations, and then you just sum up those totals. So you'll see later here when we look at the data how I did that just in Excel. So I built this equation into an Excel spreadsheet, essentially. Yeah, so we all did this in class, so we should have a pretty good idea of what went on there. So kind of stepping back out to the data here. Again, remember, we're working with these 2 different soils, Sparta and Hanlon. Hanlon, generally higher organic matter. I'll kind of give you an idea of where I would derive information about these soil series. There's a wonderful web product, probably all heard of Circle Soil and some of the Iowa-centric products, but California UC Davis has a wonderful soil center that categorizes many different soil names from all around the United States. So what you can get from these here is just a series description and kind of the word form. This is what you see with a lot of GIS products. When you download soil data in this very text format, you have to be familiar with some of the soil descriptive, kind of physical and color characteristics. And then you also probably want to be relatively familiar with the kind of general taxonomy or how that's approached, give you an idea why. So for the Sparta soil that we're looking at here, we can look at some lab data, and this is pretty well populated, so 40 pedons, so it's 40 soil examples that somebody in the world either probed down or otherwise obtained and then analyzed for these various properties that we'll see here. When you look at each of these boxes, of course, the top is describing what the heck characteristic, either physical or chemical property that they're looking at there. And then this percentage here is how many of this total 40 pedons contributed to that data point. So as you go down in this soil profile in depth, so from 0 to 200 centimeters, you kind of start to drop off in the quantity of pedons used, probably because some of these stopped at, let's say 140 centimeters. Some of these aren't populated, they just didn't have data to fill in there. But what I want to show you here is we have some CEC and base saturation, and even some calcium carbonate equivalent, aluminum saturation, some different potential clues as to what this soil might look like. So compared to our Hanlon, this is going to be a little higher sand content. We're kind of quite a bit lower organic carbon overall. We'll see we're here down well below 1 kind of throughout most of the profile. pH down by 6, a little bit lower pH. So that might indicate there's some acidity, along with some of that aluminum saturation, which drives some of that acidity. Base saturation, a huge range. That would be important when we look at what our results indicated from our acid titrations that very quickly turn pink. And then CECs all pretty much down below 4, somewhere around 5 or so. So that gives us an idea of some of the physical and chemical properties. There's also some pretty cool general information on water balance, other soils that are similar, which came into play here when I was looking for Hamlin. This thing's pretty empty. There's only one pedon. All it is some sand, silt, and clay data. Now we'll notice it's sparse, right? So only one example here, a little bit higher pH potentially. This seems like it's probably a pretty extreme example where there's some sort of sandy surface going down pretty drastically. Who knows how many actual sample points were derived there, but that's okay. So instead of trying to guess and fill this blank page in here, I decided, sometimes a strategy used here, so I go to the sibling summaries. So Hamlin here has a sibling right next door called Spillville. I happen to have spent a lot of time thinking about Spillvilles because that's the soil, for those of you that visited my flume experiment, that we've got stacked into that flume there. So it's a immediate sibling, pretty similar. Both have an A1 horizon, A2, just some difference in thickness. They're both cumulocapluloid haploidols, excuse me. So they're some kind of wet adjacent soils, pretty productive. We kind of go down here and look at similarities between Hamlin and Spillville. They both kind of fall in the same ranges in regard to things like elevation, effective precipitation, so on and so forth. So we're going to use that soil, which I've got in another tab here, which has 8 pedons, so a little more data. And we see here, okay, so yeah, a little bit less sand than our 90-ish% of Sparta. We're down in well below anywhere from, who knows how deep the soil is, probably superficial, I guess top 20 centimeters. So probably in the 40% in the Spillville, which again is kind of a sibling of that Hamlin soil. So we've got higher organic carbon and organic matter. We're well up into the 5-6 range. Higher pH, we're pretty balanced at about 7, hopefully. And then CECs. Now we've only got, I'm guessing it's 12%, so that's probably one of the 8, right? So we've got somewhere in the ballpark of anywhere from 15 to 35, depending on how deep. Up near the surface where those organic matters are, you probably have a higher cation exchange capacity. But base saturation, if we take a look at that, pH 7, which is what our soil pretty much was, close to 100% in this soil, which might explain the almost total lack of exchangeable acidity that we saw in those very quick turning pink titrations. Okay, so with all that being said, taking a look at the Sparta, that sandier, lower CEC soil, our Hamlin or our Spillville, which is kind of our surrogate in this case, higher CEC, higher organic carbon, pretty high base saturation. We'll take a look at our data here. So I did this kind of prior to doing any of the experiments with you guys, just to get an idea of what we should expect. Kind of gave me an idea of like, okay, we're on the right track as we're doing the experiment. So again, if you recall, that device that we used outputted these slopes as well as these y-intercepts, so we can kind of back calculate our milligrams per liter from our Malic 3 extract from the either absorbance or emission, depending on which of those base cations of interest. So this is a kind of a clean copy because it's easier to look at in a video, but I've got all my calculations in a back sheet here. It's a little dirtier to look at, but you can see some of those longer decimal places that we needed to kind of fill the range of that AA, which is a fairly accurate piece of machinery. I just trimmed some of those decimals in this view here. So our Hamlin soil, hopefully it's easy to see in the kind of goldenrod yellow there. We had a total of 9 samples across the 2 classes in the various groups. I used the exact same soils, so hopefully we maintain, and you'll see we did a pretty good job of keeping our variability down. So each of those samples has a corresponding absorbance for the 3 base cations and then the emission for potassium there, the remaining base cation. Those were bounced through each of the respective line slope equations, and then it just outputs whatever the corresponding milligram per liter concentration is. And then we do one more bit of converting here, and we get to a milliequivalent of soil. That was that long equation that we had in white that varied by each of the different valences and atomic weights. So that's built into that next kind of cell jump. So for example, this H1 soil for calcium, this sample is the only thing that we outputted it from a device. Everything else kind of moving across is calculated either through that slope from our standard curve or alternatively through just a unit conversion from milligram per liter to millit equivalent per 100 grams of soil. Each of those four ending milliequivalent per 100 grams of soil cation exchange capacity concentrations is totaled for that soil sample. You'll see most of the Hanlon soil totals ended up around 15. I think we had low as 14.9 and 16.15, so pretty tight range there. And then the Sparta soils, much lower, fours and fives, mostly fives. So for each of those, I just kind of grabbed a corresponding mean and dumped it down here and then totaled up those means. I did a little quick calculation on some coefficient of variance. So if you want to look at my way, you can do that quickly in Excel or Google Sheets. Take the standard deviation divided by the mean, and you just multiply that by 100 to get to a percentage. So coefficient of variance should give you an idea of kind of the variance within each of those, in our case, samples of our cation exchange capacity in milliequivalents per 100 grams of soil. So at this point, this is kind of half of the picture, right? This is the base portion. We have the titrations that we did after barium chloride extract. For both classes, we tried a normal diluted sodium hydroxide that we titrated against, as well as a kind of a hyper diluted, which accuracy at 0.002 normal, and the equipment and scales and burettes and things that we have is pretty questionable to begin with. But I will say I did notice a slight pattern in that of the titrations that potentially might have worked, those kind of hyper diluted concentrations. I'm exaggerating a bit with the hyper, but they showed that the Sparta had a tiny bit higher on average. So like patterning wise, the Sparta required a little bit more of that dilute sodium hydroxide to titrate to the pink. But in reality, they were both almost less than 1/10 of 1%. So I kind of racked my brain about that. I have zero history of these soils, but one thing that occurred to me, if you look at some of the lab data, at least of that Spillville, base saturation of 100% would essentially say that the total here in each of these is the total amount of bases, which is also the same as the total capacity of that soil. So all spaces are occupied by bases, essentially. So exchangeable acidity in the case of our soils is essentially zero. Now, I would have expected the Sparta to have some appreciable exchangeable acidity, I guess is maybe the way I would say it, for a couple reasons. So here we see kind of that running mean of those 1/3 of the 40, so a good portion, maybe 12, 15 different soil samples or pedons that contributed, but most of those are kind of down in the almost 50% range. So we'd expect the other 50% to be made up of exchangeable acidity, as well as this aluminum saturation. I don't know exactly, say a couple different reasons potentially here where you could have a case of our sample could have been managed pretty heavily. So maybe they dumped a whole bunch of lime on it right before we got our hands on it. in the era of 3 to 15 years ago, whenever it was harvested. We don't know exactly where in the landscape it was taken from, so it's hard to say. But generally, they're reducing acidity present, especially in that sort of soil. So can't really give you an exact reason why there, but that's kind of my hypothesis at this point. We'll talk a lot more about that next week when we get to calcium carbonate equivalent and liming and what that is doing to the soil. And it can maybe help explain why we didn't see a prevalence of exchangeable acidity in our soil. If you have any questions, please bring them to class this coming week. We're going to do a lab on exchangeable calcium carbonate equivalent, basically looking at the quality of different liming products and how they can modify the relationship between the soil, its ability to hold on to the various constituent nutrients that are of interest to plants and in turn us. Apologize for the back and forth with our schedule and the weather and everything, but I am no longer planning on leaving for any conferences this semester, so we should be good to go there. Look forward to seeing you guys in class, and thank you for your patience.